So as promised, we are starting a new big topic, homology. So as promised, homology will be some sort of invariant associated to topological spaces valued in abelian groups. To define it, so we need first preliminary definitions. So first we want to formalize the notion of what's called standard and simplex. So we can define it as a subset of points R(n+1), we satisfy the following condition. There's the sum of the coordinates is 1. And that's not all, and they are all non-negative. Okay, so how do they look? So delta ZR, of course, it's just 1 point, and delta 1, because this is just a T0 in R such that it's equal to 1. So delta 1 is the following subspace in R2. It's an interval. And delta 2 is the following triangle. C, and so on. So of course, delta 4, so it's hard to realize it as a subspace, hard to visualize it as a subspace in R4, but of course we can also, it's homeomorphic to standard, so delta 3, to the tetrahedron, in 3 dimensions, and so on. So it has it's a simplex which has n+1 vertices. So the definition of a simplex. So the vertices are points in Rn+1 is the following coordinates. Configurations of points here where only one of them is 1 and all others are 0. So this, for example, is just V0. Here we have V0, V1, V0, V1, V2. And so using this, the vertices, we can alternatively define it the n simplex as follows. So it's all possible points. So Vi, if I now understand Vi is an element of Rn+1. So the points in the simplex, in the n simplex, they are all possible linear combinations of Vi's with coefficients satisfying these conditions before. And of course, this using this Using this presentation, we can generalize this to any set of points in this Euclidean space 1, 0, and 0 and linearly independent. And so in terms of vertices, it's useful to use the following notation for the simplex. So we can denote the simplex with vertices V0, V1, and Vn with the following sequence of vertices in square bracket. So you can understand these guys as an element in Euclidean space, so they are determine this simplex completely. And what's it be important to keep a track of order of this point. So it's an ordered sequence. So when we choose it, when we're talking about simplex, we always keep in mind that there is a particular order on the vertices we choose. Of course, any n simplex has m minus m subsimplices. Which are just obtained by a restriction when I put I put m of n coefficients here to be 0. So this, in terms of the bracket notation, this would mean that a simplex simplex, so this hat, you're probably familiar with the notation. This means that I exclude an element of the sequence, I exclude the vertex with index I1, I exclude the vertex with index I2, and so on. So I am, and I keep all vertices this way. So this simplex corresponding to this sequence is embedded in the original. So, for example, if I have a 3 simplex with vertices V0, V1, and V2, so this contains I have, for example, V0, V1 inside the V1 simplex with vertices V0, V1 inside these 2 simplex, and this just corresponds to taking this H as it has.
Yeah, in the representation of delta 3, it should be a subset of R4, no?
Yes, but as I said, it's hard to draw R4. That's why I just. But you also can. Well, as for example, here is the triangle. Okay, you write it as a subset in R3, but of course you can also embed triangle in a plane. Like here, I can always. I can, in principle, like this, realize in R4, but of course it's homomorphic to a tetrahedron. It is homomorphic to some tetrahedron in 3 dimensions, which I can draw.
The length of the file tell us the dimension where we are thinking, or I mean the length of the data range tell us the dimension of the environment? Or? I mean, you put some hat, but why don't you simply don't mention those elements? Not look over there. Look here. Is it the same to write the hats, the tilde?
So the hat means there is no. I remove this. I remove the hat. I remove this vertex. So this, in this, for example, sorry, V1, V2. This is just this notation. There are some sequence to denote that I remove this element. I write a hat. This means that if I write hat, this means it's not some other vertex. It's just the same vertex. This means that this vertex is removed from this sequence. Any other questions? Another definition is the following. A delta complex structure on a topological space X is a collection maps sigma alpha so each map is a map from n simplex to X for some n, so n depends on alpha on this index. For different indexes, there are generically different dimensions of the simplex. Satisfying the following properties. So there will be 3 properties. The first property is the following. Sigma alpha, if I restrict sigma alpha on the interior of my simplex, so currently this means the interior, of course, is the same as simplex itself minus its boundary, because for simplices will closed subsets. Is injective. for any, and moreover, for any point x in my topological space, there exists a unique alpha such that x is in the image of this restriction of sigma alpha restriction of sigma alpha on the interior of the simplex. So this essentially means there is a one-to-one correspondence between points in X and interiors of this collection of simplices for all the indices. And second property is that if I restrict sigma alpha on a face of delta n, so the face means this is n minus 1 subsimplex. So space is a particular case of some simplex that we considered before. And so this was an example of a face. And so this state means that this is equal to this restriction is actually the same as this map is the same as sigma beta, which is a map from delta n to x for some other for some b. Okay, and finally, the third property is that A, if I take a subset A in X is open if and only if its preimage for any sigma alpha is open in my simplex.
Isn't it just positive?
If and only.
Ah,
It's strong.
yeah.
In particular, this last condition essentially implies that, well, if you know, I mean, the topology on X can be reconstructed from this topology on the simplices. And so the meaning of all this, so these three properties, they formalize essentially the following statement, which the following statement, which you can say in words. X is obtained as a topological space by gluing of simplices along faces.
The dimension of the samples is fixed.
Hmm?
The constant, the dimension of the samples.
No, this n they vary. They can depend.
I can depend with alpha.
Yeah, that's what I'm saying. They depend on.
Okay.
Of course, it's not well only for a point. Well, let me give you an example.
Equation first. What's the topology for the interior of delta n? Because it is close in the definition.
Yes, so you remove all the boundary points. You understand the subset, closed subset in Rn+1, so you can remove all boundary points. It's like, for example, for in one dimension, you take an open interval.
It's not the topological interior, right? It's not that. It's not the topological interior. It's.
Well, this.
But you're right.
This.
Yeah.
Because if we take the boundary for the topology of Rn+1, it's solved because it is closed.
Because it's closed, I can tell you. So we mean it's geometrical boundary, not topological boundary. Except if the dimension of the simplex is equal to the n+1. In that case, it's topological, but the other. Like for example, if we take a square in R3, then the boundary is the square because it's empty interior. That's what he meant, I guess.
Yeah. Well,
It's a geometric boundary.
well, the boundary. Okay, it's a boundary if you embed it into if you embed it in n-dimensional space, not an n+1 dimension.
You can always embed into n-dimensional space.
Yes. Because you always, I mean, all these points, they lie in a Rn in a subspace. Rn, which is just given by the condition that sum of these guys is 1 inside. Well, let me. I can just formally say that this is the Dn is that is where the boundary by boundary exactly means just the following set. It's one of Ti's is 1 at least. Sorry, wait, no. I think it's what I want to say is 0. So interior means the points in the definition where neither of. So yes. Looking into the following example of torus. What is the example of delta complex structure of torus? So we know that the torus can be realized as the quotient of the rectangle by equivalence relation, which identifies squares with edges. We choose a delta complex structure by this. By just triangulating this rectangle. So first, so I have to choose which will be maps of two simplices. So be this would maps would be, let's say, sigma 1 and sigma 2. Sigma 1 and 2 is a maps from delta 2 to T2. And so here I kind of use notation by the same letter denote the images of those maps. And then let me take sigma 3, 4, and 5, the maps from delta 1 to T2. And here, well, this will be sigma 1. So one simplex is just an interval. This is the same, it should be the same sigma 1. This should be sigma 2, should be sigma 2. Oh, sorry, sigma, what am I doing? Sigma 3, sigma 4, sigma 4, and here let's say sigma 5. And there will be a single mark from 0 simplex, whose image is just this point, which is the same point. Sigma 6, sigma 6. Essentially, you can understand as a triangulation. It's not high-dimensional arc of triangulation. And of course, it satisfies all this condition. So in particular, example, we want, so one of these conditional restriction is that sigma 2 restricted. So first of all, this is of course satisfied. You see that if you just take interiors, for any interior, there is one-to-one correspondence between the points in the synthesis and points in the torus. I mean, you see, we have to take interior because otherwise, if we take this point, this is not going to be unique alphas, both realized in the image of sigma 1 and sigma 3. That's why we have to take interior. But it also wouldn't be injective because we have on this point, they mapped to the same point, points on the boundary of this. Okay, and so what about this? So this restriction also works. You can see, for example, just in the example, sigma 2, if I restrict sigma 2, so let me choose the vertices here. I have to pick an order of vertices of this sigma 2. So this is 0, 1, and 2. I mean, this is the images of the vertices in delta 2, labeled by 0, 1, and 2. And then, for example, if I restrict it to this face, V0, V1, this is the same as sigma 5. And of course, one can check it for all other faces and spaces. Questions? Okay, now another definition for questions at the beginning. Let me see where we make all the definitions. So this is delta n, depending on x, my topological space. This will be a free abelian group generated maps which appear in the delta complex structure on X. In other words, the set is just a set of formal sums where m alpha integers. And of course, the addition is done by adding up the coefficients. And one have to also make the following remark. So how, I mean, so we mentioned that this simplex, when we talk about simplexes, we usually pick some order of vertices. And we have to say how this choice of what is dependence here in my abelian group on the choice of order, on the choice of which corresponds to choosing orientation of the simplex. Order of the vertices. And the dependence is such that if I take any simplex, so if I consider map on some simplex with some vertices, with some chosen order, and if I swap pair of elements, if I do a permutation of two elements, this corresponds to taking the same thing with the minus sign. Of course, using the transposition of two elements, I can relate for any permutation. I can relate the signals. The results only depend on the parity of my permutation. I will also use for this for the formal group, for the free abelian group generated by some elements. I will also use this the angled brackets notation. So before it's a bit overloading of notation, because before we use this brackets to denote a free group generated by the corresponding elements. But here we use the same as for free abelian. But since from now on we are going to talk about abelian groups, so this is not going to shouldn't cause any confusion.
Sorry?
Yes.
What do you mean with minus? Because sigma is a function to x, no?
No, I mean in this as an element in this.
Okay.
You mean one.
What's exactly
Is the same.
What's this linear combination?
It's a formal sum.
In the
It's
sense?
not.
In which sense?
Well, it's a free abelian group with generators. Each generator corresponds to each sigma alpha.
I mean, clearly this is just a set at the end, delta n of x. So which group law that makes it free? group.
Well, the group law is that
So it's given like that from.
questions. Generally, if I talk about free abelian group generated by some elements of some set, this means I can say the formal sum of the elements of this set with coefficient being integers. With this also generates.
Or the product, could you?
Hmm?
It may be the product of the powers. It's not.
Product.
I mean, this is just notation.
Yeah.
We can do the product of the powers instead, if we want.
Product of the powers.
Yes.
Yeah. Yes.
That's what I was confused because we don't have they use.
Yes. Yeah. We use kind of additive.
Yes.
Additive. Essentially, what was 1 before will be 0. So now I can raise the notion of boundary homomorphism. So it's a homomorphism between delta n of x and delta n minus 1 of x. These are abelian groups. Say that, well, since it's a free abelian group, it's enough to understand what will be a result of homomorphism on a generator, on any generator. So let me take any generator here. So the generator is a map from the n simplex to x, and the result should be a linear formal linear combination of maps from n minus 1 dimensional simplex to x. And this sum is the following. I take the following combination sum from I equals 0 to n, and in the is term I remove. I consider I take this simplex. Let's say it has vertices v0 to vn, and in the is term here I remove the is. I consider n minus 1 simplex, where I remove is vertex, and I consider restriction of this map to this n minus 1 simplex. So this does give me a map of this form, and then I weight it with this integer number, which is just minus 1 to the I.
So in the definition, we assume that all the generator has the same dimension n. I mean,
Yes. Here for any, yes. Here n is because we fix n here, so n is fixed. here we only consider alphas for fixed n. Of course, we can consider kind of direct sum of these abelian groups for all n's, and then this will be all just a combination, just formal sums of all sigma. Here n is fixed. So this boundary homeomorphism has an important property, which is essential property for all homology series. The following composition is a trivial homomorphism. The composition is the following. So if I want to draw a diagram, this is a composition of the maps. Like this. So the composition is a homomorphism from this abelian group to this abelian group, and the second is this is trivial. We improve this. So again, it's enough to check this on an arbitrary generator of this group. We take some sigma alpha here. By definition, so let's see. So let me first apply this. Boundary homomorphism. Here I just use the definition. Okay. And now let me apply this homomorphism on the guys here. The homomorphism for abelian groups means that it's a linear map. I can interchange the sum and the action. So if let me just immediately write. So I apply for each I, I'm going to apply dn minus 1 on this thing. So what should I do? I should consider all possible removals of the vertex of the vertices in this sequence where I already removed each vertex. So to do this, first let me consider the terms where I remove some of the vertices in this before this guy. So first there will be sum from g from 0 to I minus 1. So I have to rate it by this minus 1 over j. And before sigma alpha, and I remove j vertex here in this. And then there are separately, I want to consider the terms in the image where I remove some of the vertices after vi. The sum, the j goes from I plus 1, so it's after I to n. So let me first write the restriction. So it's restriction to V0. I remove Vi and then Vj. And I have to notice that this is so since we skipped. We already skipped one vertex here, so this is going to be not -1 to the j, but it's going to be -1 to the j minus 1 instead. Because this position is actually j minus 1's position, because this guy is already removed. Here it was j's position, but here it's position j minus 1, from if I count from the beginning. Okay, and then, well, let me. Now I'm just using some algebra, so let me just combine these sums together. So for the first term, if I combine the sums, I can write this sum as a sum, as a sum over pairs where g is less than I, right? So the coefficients will be I plus j minus 1 I plus j, just multiplication of these two things. And then there will be sigma alpha okay, and I do the same for this guy. So this will be this is written as this can be written as a sum over pairs where j is greater than I. Coefficients will be -1 to the I plus j minus 1 sigma I, and here I remove Vi and then Vj. But now, of course, I can just this is just some labels over which I sum. So of course, this I can exchange. I can redefine my indices here so that I swap I and j. This will be the same, everything will be the same except this extra -1 here. So these are actually cancel each other. So this is will be just minus this. If I just redefine a change my acceleration measurement. Questions? So another definition, so this will be a general definition which we will use sometimes. So a sequence, the sequence of the following form. So it's going to be a sequence of abelian groups and homomorphisms between them. Abelian groups Cn and Holmes delta n such that, so here I'm talking about some abstract situations of the delta n is not necessarily as defined before. This is some abstract homomorphisms such that we want them to satisfy this condition, if I take two consecutive homes, the composition will be 0 for any n. And so such segment is called chain complex. So to notation to denote the chain complex, usually I think we will use C star. C star means that there is some index here which runs from 0 to, well, in principle to infinity, but in most usual cases these groups become trivial after some sufficiently large n. Or sometimes we can denote just by C, these segments. But of course, you have to keep in mind this contains not just these interwaves, data contains not just the groups, but also the deeps, the homes that are part of this data. And so whenever we have this condition, so currently this means that the image of dn is the same as the kernel. Sorry, the image is in dn is inside the kernel of dn plus. Dn minus, well, image of dn plus 1 is inside the kernel of dn.
Equals to 0.
Yes. So using this property, we can define the following group. So another definition, well, the definition which kind of relies on this definition. So the billion groups HN, so a billion groups associated to a particular chain complex, and they defined by considering the quotient of the kernel of dn, so the image of, or the image of dn plus 1. So this is well defined because this is a subgroup inside here, so the quotient is well defined. And the definition says that these groups are called homology. Groups of the chain complex. So this is a very general notion. So whenever you have this structure, you can define these homology groups. So now, we have now we can return to our particular case. So we do have this structure where CNs are delta n's, the groups we defined before, and delta n's are boundary homomorphisms, which we defined before, and we proved in that situation we do have this property. We can apply this general construction to our case. So, in the case like Cn delta n of x, as we defined before, and delta n boundary homomorphisms, as as we defined before, in this particular case, these homology groups, which will denote H delta n of x. So for given n, this is called simplicial homology of x. Of course, here it's important that it's not just depends on x, but it depends on the choice of this delta complex structure on x, which roughly one considers triangulation of x. And, so let's see what happens for our example, which we considered before, when x is T2. Okay, so let me see. So we had this delta complex structure. So this was, I'm not sure if I'm using the same indices as before. This is sigma 5, and this is sigma 6, sigma 6, sigma 6, sigma 6. Yeah, I'm not sure this is exactly the same numbering. Before. So let's see. So what is the first? We need to determine these groups, right? And so what about, we only have maps from 2, 1, and 0 synthesis. So then I consider n 0, 1, 2. So delta n of x will be generated by sigma 1 and sigma 2. Again, here, this generated means it's a free abelian group with the generators, which is all possible formal sums of these two guys. And so this is essentially, well, as a group, this is homomorphic to z squared, right? Just two generators. And delta 1 of x is generated by sigma 3, sigma 4, sigma 5. Isomorphic to Z3, and so it's just a single generator, and this is isomorphic to Z. So far so good. So we determined these guys. Now we need to determine how deltas act between them. Okay, let's start with D2 is a map like this. Of course, we know the n for n greater than 2, they are just identical yet. There are no high dimensional synthesis. Okay, so again, we need to see what happens with the generator. So what about D2 of sigma 1? Okay, so I need to, now I need to be more careful to get a correct size. I need to pick order, choose order of the of the vertices. So for sigma, well, let's say for sigma 1, I choose 1, 0, 1, 2 here, and here I choose 0, let's see, so it's really 0, 1, and 2, also like this. You can see with this choice, all orders will be consistent. So this 1, 2 is consistent with 0, 1, the same. Same order. Okay, so if I take the sigma 1, so what I need to do, so I need to start removing vertices. So we're starting with vertex 0. So if I remove 0, so I get this space. And here is a restriction of this space is sigma 4. And then I remove this vertex. I get minus, I should take minus sigma 5. And if I remove the last vertex, I get plus sigma 3. Just using this the general definition before. And okay, I need to do the similar things for sigma 2. So I remove 0, I get sigma 3. So here, we know that it's a product here because sigma 3, I take it's sigma 3 taken with the same sign as here, because here, if I took the order here it was the order like this. This vertex goes after this in the ordering of vertices here, and here it's also the same order because 2 goes after 1. And then so if I remove 1, I get minus sigma 5, and then I get sigma plus sigma 4. Right. So I see this guy is actually the same, right? The result of the boundary homomorphism of sigma 1 and sigma 2 is the same. In particular, this means that d2 of the difference is 0. And so in particular, I see that the kernel of d2 is generated by just a Freiberling group generated by this difference, which is isomorphic to Z. And now I already can, since we know that the image of D3 is of course trivial, the image of D3 is trivial, so I can calculate H2 delta of T2. So this is kernel of D2 divided by the image of D3 is Z divided by 0. So we calculated H2. Okay, so now we determine this delta 1 map D1 from delta 1 to delta 0 of x. Well, x is T2 for us. So again, we need to determine it on the generators, which are sigma 3, sigma 4, and sigma 5. for sigma 3, okay, so this is, so we need to again remove remove vertices. So if you remove starting with this, the order was like this. If you remove this vertex, so we get just sigma 6. And if you remove the second vertex, we get all this sigma 6, but we have to keep in mind that we should alternate signs when we take the this boundary homers. It's actually 0. And yes. And you can see the same will happen for, same thing will happen for other guys. Sigma 6. So in particular, this means that the kernel of D1 is just the whole space generated by sigma 3, sigma 5, which is 3. And we also know that the we know that the image of D2, this we already know, the image this is just Abelian group with a single generator, like this. And then it follows that now we're ready to calculate H1 X. This will be well, kernel D1 divided by the image of D2, which is Z, divided by Z. Squared. It's we quotient this group by this by subgroup with a single generator like this. Currently, you can write as a group with 2 generators. And okay, so finally, we need to consider D0. So D0 by definition is just 0, right? There are no -1, no -1 simplices. And okay, so the kernel of D0 is generated, Abelian group generated by this sigma 6, which is Z. And we need to gonna quotient it with respect to image of D1, which was well, trivial, right? Nothing. We don't have anything in the image. So this means H0 delta of X is well, kernel divided by the image, which is Z divided by 0, which is so the result, summarize the following. So for n equals 0 we got Z, for n equals 2 we got, sorry, n equals 1 we get Z squared, for n equals 2 we got Z, and for all higher hence we got any questions?
It depends really in delta. I mean, if we
the result, yeah, the result is not going to depend on delta. In principle, the result is not going to depend on delta, but we're not. Well, we're going to take a different approach to defining homology. But yeah, I will comment. Yeah. So if there is no question, then I leave another example of the exercise. Take x equal to RP2. And similarly, you know that RP2 can be realized by this quotient of a rectangle, where instead I identify this edge with this edge, but with opposite direction, and similarly this edge with this edge with opposite direction. So of course I can use this to I can triangulate it like this. So if here provide me some delta complex structure, and one can calculate that this delta complex structure the homology groups. And if you do this, you can find the result with the following. So for n equals 0, you get z. For n equals 1, you get this z2. And for n equals greater than 1, you get 0. Essentially, the idea is to repeat, to apply, to use the same technique. But here you see there will be one step point, so you get something. At some point you get something like, how do you get this Z2? It's over here, some sort of quotient of you have a group generated by some free group with some generator A, and you end up at quotient by subgroup which is generated by the twice as generator. So this is something like this. You can produce Z2. Now, like the following remark. So we defined some sort of what we defined what we call the simplicial homology, but it's in a certain sense this is a bad thing. It's bad because it requires. The definition requires a choice of additional structure. Of X. And it's bad in a certain sense, so it's actually, it's hard, using this definition, it's hard to prove theorems. But it's easy, as I saw, it's easy, very easy to calculate. And there are a lot of problems, to develop a theory for this, there are many problems, because first of all, not any topological space X can have this delta complex structure, and if it does, yes, you have to show that if you want the result to be a topological invariant, it depends on the homomorphism class of your topological space, you need to show, every time you need to show that this doesn't depend on the choice of this delta. Nothing depends actually on the choice of this delta complex structure.
So what does this cylindrical homology measure?
Well, it measures roughly number of certain cycles of certain dimension, closed loops, and roughly closed cycles. Well, we will talk about this a bit more. But again, roughly, this is for a given n. If some generators, they correspond to the holes of the dimensional space. So in particular, H1 is what is closely related to pi 1. To be precise, this H1 is a billionization of pi 1. So when this group is a billion, it's actually the same for path connected space. But the point is that we're going to use a different. We're going to introduce a different what is called singular homology, and it's actually well, we're not going to have time to show it, but the singular homology which we introduce is nice to kind of. It has a nice definition, so it doesn't depend on any extra structure. It's easy to prove various theorems, but it's hard to calculate. But nevertheless, one actually can show that they are, in good cases, this is the same. The result is actually the same as the simplicial homology. But yeah, this is. We actually define. We're not going to use this definition anymore in our course. But I wanted to introduce it to just because it's easier. This is an example where it's easy to get a feeling of what homology is. And, so for torus, so if you want to ask the geometric meaning for the torus, so this H0, which we had Z, it was corresponding to the fact that there are the kind of points. It's just a number, so we will show in general, which the number of generators of H0 is just the number of connected components. So we can answer the points up to kind of different dimensions. So H1 will be Z2, and generators, they, in a sense, correspond to these two loops like this. And H2 is Z, it was kind of corresponds to the whole space. This a cycle. Two-cycle which wraps the whole space. Anyway, this is just some intuition. So I'm not making precise statements. So we want to make a different definition. So let X be a topological space. And so we want to define what's called singular chain complex. So Cn. For a chain complex, we need to define a sequence of abelian groups. So the abelian groups will be 3 abelian groups. generated by all continuous maps sigma delta n to x. So there are no other restrictions. So it's a very crazy, well, of course, in general case, there's an infinite number of generators. You can consider a lot of different maps. So before we only had these maps which enter in this delta complex structure, but now here we consider all possible maps. Okay, so now we want so the part of so we want to define the boundary homomorphism. From Cm minus 1, and it will well, it will be defined essentially by the same formula as before, as for Simplicio chain complex. So the generator here is some arbitrary continuous map from delta n to x, and so again, if I choose my delta n to be labeled vertices by v0 to vn, the result will be this alternating sum. Of course, well, this property will be still satisfied. This is so proof is essentially the same as for Simplicio. Okay.
Excuse me, I don't really see what's the difference.
Well, there the maps which was generated for the maps in this in the delta complex structure. The delta complex structure gives you some set of maps from simplices to x which satisfy certain conditions. It was a part of the structure. In particular, in those examples, there was just finite number of maps for each m. Here, this is all possible maps, whatever you want. This well, you don't use any additional structure on x.
Every topological space has a delta complex structure.
No. Well, I mean, all Mach spaces have manifolds. They all have complex structure. Okay, so we have this. We have a chain complex, and so we can use the general construction to define the corresponding homology, which we call singular homology of logical space X is chain is just known by a chain of X, there is no this delta symbol, because it doesn't depend on any additional structure. And so they are defined as homology of this chain complex, which the general definition is this ratio is a quotient of the kernel of the image. When I talk about singular homology, or actually homology in general, there is a certain terminology which we can use and we also will use. So if I consider just a map, arbitrary continuous map from delta n to x, so this is one of the generators. Like all generators, so this is some generator here. Is called a singular simplex. Singular, because it's n simplex. So why is it called singular n simplex, this map? This is because this can be understood. So we have some map from some simplex to x. So unlike as in this in the delta complex structure, there was a lot of nice conditions of the particular. There is on interior there was one-to-one correspondence to the points in x, which essentially meant that there's some sort of nice inclusion of this simplex in x. But here there is no condition like this. For example, all the image can be some sort of very degenerated simplex version of the thing. So, for example, they all can degenerate to just some sort of interval like this. That's why it's called singular. And so but like any element, some arbitrary element of Cn of x. Well, sometimes I'm not gonna usually write it, but I can introduce a explicit dependence on x. So it's called is an n chain, or singular n chain. And but if in addition we have the condition that the dn it's in the kernel of the boundary homomorphism, then we call it beta is an n cycle. And beta is in the image. It's of boundary homomorphism. Then such n chains called n boundaries. So using this terminology, one can informally, with this precise thing, one can informally write that this Hn of x is a quotient of well, the abelian group generated by n cycles over n boundaries. So maybe to give you some sort of geometric notation very roughly. So I mean the n chain, so if you have some x, the n chain looks well, general n chain is just some some crazy linear combination of this singular simplices. There is nothing nice about it. But if it's n cycles, this means that the kind of if I take a boundary operation for different kind of elements here, they will cancel each other. So this means roughly this is sort of looks like a bunch of, well, all simplices they can be weighted by some numbers, but the kind of when the boundaries coincide, these numbers should add up with certain signs. They should add up to 0. Yeah, I'm not sure if this is anyway. Oh, this is not how you usually calculate this. And so this is roughly how this. Well, in this particular case, it's a two cycle. Looks like. And but you want the quotient. The quotient over n boundaries means that you can essentially, for example, replace if you have some sort of you have some sort of pairs. For example, if you have pairs of faces like this in your chain, you can replace it by you can replace these blue faces to the pair of orange faces, right? Because the difference would be a boundary of this three bound. So it's a two bound.